we need to talk about the pledge problem. So we didn't think we were going to be able to come up with a single pledge problem that covered both rotational motion and fluids. But we don't want you to be disappointed, so we really dug down deep and we came up with one. And as you've seen, it's the jelly dispensing machine that has, let me get a quick drawing going here, has this circular wheel that spins at a constant rate, but attached to it is an arm. And you primarily care about the position of two things. The position of this pin that rotates, that kind of moves the arm around, and the position of this pin that pushes the piston, that pumps the jelly. So, standard pledge problem has lots of questions. There were a few little things about rotational motion we didn't cover in detail on kinematics. So I want to give you a few tips about that. And then also how to do an expansion and use that in physics. We don't use that too much in the class. You need to do it here, so I thought, well, let's go over it a little bit. You'll see it's not the end of the world. Okay, so let's just start going through them here. So A, the first thing it asks is, what is phi, the angle of the position of that pin as a function of time? Because that's going in uniform circular motion. Right? We were told that the disk is at a uniform rotation omega, and we were given a coordinate system that is very conveniently centered on the disk and follows the standard rules of plus x there and plus y there, and even defines the angle phi, which we would normally call theta, but we switch things up sometimes. In terms of phi is 0 here, and it's positive that way. So we're following all of our normal conventions. So if you're asked, let's see, so A, expression for the angular position of the disk pin as a function of time, you would need to go back to the kinematics. Now remember, we said rotational kinematics are just like translational kinematics. We just wrote on the formulas and moved on. We haven't used them a lot. I think in the space station problem, you had to really think about how much rotation has it gone through. But if you want to use them, let's think translational first. What's the equivalent situation translational is constant velocity. So you say x, the position, is the initial position plus vt. So for rotational, the final angle, in this case though we're calling it phi, is whatever initial angle you had plus omega t. So this would be phi as a function of time, but we probably want you to plug in the initial position. So what we're saying is, at time equals 0, it started with the pin over here. So you just need to put, how many radians is that if this is 0? Put that number there, plus omega t. And you're done with part A. See? Not so bad. And then part B, it says, now give me the Cartesian version. Give me x naught of time as a function of time. This is as a function of time, by the way, I just didn't write the t. And give me y naught as a function of time. But since we're following standard definitions with our x and our y and our phi, then it's just following the standard rule that it's whatever the radius is times the cosine, or in this case phi, and whatever the radius is times the sine of phi. And I think we're even calling this big R, so that matches. So pretty much just putting these in here would be your time-varying x position and your time-varying y position. So really A and B is mostly geometry. I'm just letting you know that all you need to use is constant angular velocity kinematics to be able to track that position. Let's see, what else is it asking us to do here? Let's see. Oh yeah, so now the interesting part of the problem is this is a machine where when this moves with circular motion, this kind of goes back and forth in some weird way. And it's not necessarily simple harmonic motion, it might be kind of an unusual mechanical motion, but the point of C is you don't have to worry about it. We're giving you the motion, right? So the patent told you that the motion that follows x is a function of time, not of the pin, but of the, what's the word, what do we call that? The piston pin, not the disk pin. This is all the disk pin. This is now the piston pin, that's why there's no subscript on it. The disk pin is r cosine phi, but the piston pin is this expression they give you. It's the position, the x position of the disk pin plus this square root thing, L squared minus R squared the sine squared of phi. Well, I ran out of room as a function of time. There we go. So it's right there in the problem. Even though I ran out of room, you can read it right out of the problem. And what they're saying is this does follow weird motion, and this is the motion. That's the discount part, this is the mid part. You could find it if you wanted to. If you draw the right triangle, you can come up with that. I know you can. But you don't have to, it's just given to you. So the explain part, what are we doing with it? Just think about what it looks, between, if we're going to let L and R vary, the radius here and the L there, mathematically, does anything jump out at you here? If L and R were certain values, that would be a problem. And physically, does anything jump out at you here if L and R were different values? That's all you're looking for in C. And then D is another just descriptive thing. What kind of a motion is this going to be? Just thinking about how it would move. Make yourself a cartoon if you want. Do a full animation if you want. But then E, this is the big one. Okay. E. So talks about expanding a function. And you've done this, calculus 1, you've done this stuff, but here's an example of how we use it. So in physics, we'll expand something, and often we have it in this form, 1 plus something. So here, this is binomial 1 plus b to the a approximately equals, and we're giving you the formula 1 plus ab plus dot dot dot. In physics, that means more terms, right? Because this is some infinite expansion where there's an infinite number of terms, okay? But in this expansion, these don't matter if b is less than 1. So if b is less than 1, you can keep this term. This term might be kind of big, you got to worry about it, and these you just throw away. And that's why you say approximately equal to, okay? So we're going to use this. So what's our function looks like? We're just applying it to this part. So ours is a square root. So right away, a equals a half. So if you want to use this in physics, you say it's the square root of 1 plus b. It's about equal to 1 plus, well, what would it be? ab, 1 half b. There would be other terms that you don't care about. 1 plus 1 half b is what it would be. But that's only true, what? If b is less than 1, okay? So you got to figure out how to get this to kind of look like that, all right? I'll give you an example. Let's see if this works. What's the square root of 17? Oh, you could do it on your calculator. Let's do it this fun expansion way. That's equal to the square root of 16 plus 1, okay? Kind of looks like this, except I want a 1 here. How about we just pull a 4 out? Right, divide this by 16, divide the whole thing by 16, and pull out the square root of 16. And you get 4 times the square root of, bring it in here to 16, divide by 16, 1 plus, what is this? 1 over 16. Right? Interesting. So what is that equal to? 4 times now, what is this? This is 1 plus 1 half of 16. Of 1/16. Okay. Well, we could distribute that a little bit. We could say, okay, that's equal to 4 plus 4 over 2 and over 16. That's 4 over 4 over 2. That's 1/8. That's 0.125. So we would expand this to find that it's approximately equal to 4.125. And if you do it in your calculator, it's 4.123. So very close. So, but the key was we had to pull things out, we had to manipulate it to get it to look something like square root of 1 plus something small, or something less than 1. So that's what they're talking about a lot. You just got to do it with that. All right. So let's see, that's the big one that we haven't done a lot of that, but it's a useful skill. Let's see, F, and then we're getting to some stuff here. Yeah, F is calculated torque. That's an important part of this section of the class. Just the only thing I'll say about F is your answer in terms of R, F, L. Okay, you're not supposed to be rolling on the floor laughing. Okay, you're not supposed to get a number here. Just in terms of the force, you don't have to find the force. We're just telling you there's a force F, so use the force F. And then finally, we get to the fluid parts. And you'll notice if you're really panicky, you're unhappy about this, you don't need any of this to do the fluid part. right? So like for G in the fluid part, we said, okay, you've got your setup here with your thing coming down to the jelly there like that. And you got your piston out here pumping it up, and you got your jelly down here, your straw going into the jelly. And we tell you that the pressure in here, it starts at atmospheric, in one cycle adds a P, another cycle adds a P, another cycle adds a P, another cycle adds a P. So each cycle you're pumping up the pressure by P, 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 another P, another P, another P. And you're trying to make the jelly rise up to some height where it's going to come out. Right, so nothing about all this. All you need to know is it goes around once, it adds a pressure we're giving you, P. So that's why then you would work on, I forgot what the question was, something about how many P's do you have to add to get the jelly to come out. And then finally, last question, how fast is it going to come out? For that we need the Bernoulli equation. That we're doing fluid flow, dynamics, etc. So we covered Bernoulli last Thursday, but we haven't yet covered how to deal with a case where the fluid comes out of a hole. Okay, I'm going to do an example of that Tuesday in class. It's the last little fluid thing we're going to do before we talk about waves. So be sure to see my example Tuesday that will tell you how to handle the pressure when something flies out into the air. And then you'll be able to apply the Bernoulli equation to do part G. And I love the problem, although it kills me that we're using the Bernoulli equation with no viscosity to describe jelly, but I'll get over it, and I think I'll be okay with that. Okay, so that's my hints to the pledge problem.